All right. So as I said, today we want to go over some additional things about errors and uncertainty, more focused on like the data analysis stuff that you should be doing after you have completed collecting all of your data for your Skeeter SAT calibration report. So one thing that was mentioned during the previous lecture was we said that random errors follow some sort of mathematical distribution, but we didn't really talk about what exactly that means. Well, all a distribution is some sort of function that tells you the the relative chance or the probability of getting a particular value of a measurement. So when you are making a measurement, you're basically pulling a sample out of that entire possible range of samples, each with a different probability. When you do analysis, you usually make an initial assumption about what that distribution is, and you often assume what is called a normal distribution, a normal population, a Gaussian distribution. Those all mean the same thing. And like I said, when you take a measurement, you're basically pulling a sample off of that distribution. So if you make more and more repeated measurements, you should get a better idea of what that overall distribution of all the possible values for your measurement, what they can be. But one thing to note is, in general, when you talk about a distribution, you're just talking about random errors, not the sort of systematic errors, i.e. the things that aren't random, you can't average over. So like I said, the most common type of distribution you see is something called a Gaussian distribution. It's also called a normal distribution. And it has this particular formula, and there are three constants that sort of alter the, specifics of the shape of this curve. And really, actually, one of the constants depends on the other two, so there's only two parameters you have for picking it. The first one is this Greek letter here of the x, that's called a mu, and we use a mu because that's basically a Greek m, and what that is it's the mean. It's where the center peak of this curve is. And if you average over all of the possible values of this distribution, the number you get will be that mean. So if I change the mean higher or lower, I shift the entire distribution to be centered on whatever you pick for that value. The other parameter is this circle with a little bar over it. That is a lowercase Greek sigma, and that is called the variance. And what that actually does is change how wide the distribution is. So if you have a very, very small sigma or variance, you'll basically have a very sharp peak. If it's if it's large, you'll have a very broad peak. And then finally, the constant that is out in front of this distribution is just what's called a normalization. So usually when you're dealing with these sorts of things, you're talking about a probability. So you want the entire probability total to add up to 1. So you just change that number so that the total area under the curve is equal to 1. So if you look at the graph there on the right, what that shows you is, so the red line there is the shape of a particular Gaussian that has a mean of 10 and a variance of 3. The vertical line in the middle is the mean, and then there is a dotted line and a solid line that is 1 sigma and then 2 sigma greater than or lower than the mean. And in particular, there are a certain amount of area under the curve that is within those boundaries. So within 1 sigma, you have 67% of all the total possible values. So another way of saying that is I basically have a 67% chance of getting one of the measurements within 1 sigma of the mean. And then for 2 sigma, it's 95. These aren't numbers you should feel like you need to memorize. They do sort of come up, but you know, it's the sort of thing you can always look up if you need to. So one thing we just mentioned is that distribution has a mean, and then there is also a mean of the measurements you take. And these are actually 2 different things. There's the mean of the distribution, and one thing you could think of is that's what the true mean. Sometimes you'll see it referred to as an expectation value, but like I said, it's just an average of all of the possible values in the distribution. Then you also have a mean for the sample, as in if I make a bunch of repeated measurements, what is the average of those repeated measurements? And that is not necessarily going to be the same thing as the mean of the distribution because you're pulling measurements at random. But you know, that's calculated exactly how you normally think an average is calculated. You take the sum of all the values and you divide by how many there are. But one thing to note is that average of the sample, the mean of the sample, gives you an idea of what the mean of the distribution is for those measurements. And as you take more and more and more measurements, it becomes closer and closer to what that true distribution mean is. So if I was to take an infinite number of samples, these 2 means or averages would become the same thing. And another thing that we talked about last time is that there's actually a standard deviation, but there's actually more than one standard deviation. So, and depending on if you're in physics or biology or demographics, if you just say standard deviation, people might assume you mean different things. And because of that, if you're writing a report or a paper or giving a presentation, you usually want to be, it's always better to be specific about exactly what you mean. And all that means is showing the equation, you know, somewhere in your document or on your slide. So like we said previously, there is the sample standard deviation of the mean, which is the second equation there. But there's also a population standard deviation of the mean, and then the standard deviation of the, sorry, I think I misspoke. There's a sample standard deviation, a population standard deviation, and a standard deviation of the mean. Those are the 3 different ones. And similar to the sample average and your distribution average, they're not the same thing as the variance or the standard deviation of the distribution. But they are similar in that they give you an estimate of what that true sigma for the distribution is. So the standard the population standard deviation, the key thing here is it assumes that you have all of the population. And in fact, if you look at this equation, the way that it's been written up, this includes mu, which is the true mean, but we don't know what that is, so you can only use your sample mean. But it turns out, if you do that, you will actually underestimate your what the variance or the sigma of the distribution is. How much you underestimate and how big that a concern is sort of a factor of how many measurements you take. Like we said, as we take more and more measurements, you get a better idea of what the distribution is. Your sample and distribution means become the same thing. If I take enough measurements, all of those values are going to be equal. What you actually want to use is the sample standard distribution. The sample standard deviation. And it's called the sample standard deviation because you only have some subsample of all of the possible values. So you can correct for the fact that you would underestimate the standard deviation before by just replacing the n with n minus 1. And you can tell that's always going to be a little bit bigger. But as n becomes really big, the difference between n and n minus 1 doesn't make, they effectively become the same thing. You know, 1,000,001 dividing by 1,000,001 is the same thing as dividing by 1,000,000 for most cases. Also, this sort of has a intuitive sense that, hey, if I take a single measurement, I can't tell anything about what that actual distribution is. I've just picked one random value, you know, maybe you got one way off to the side, so it doesn't really tell you anything. And if you look at the value you would get with a single measurement, you get 0 over 0, which mathematically is indeterminate. It basically doesn't mean anything. But as the number of measurements become very large, this becomes the same thing as the population standard deviation, and also both of those then become the same thing as the distribution sigma. But the key takeaway here is you want to use the sample standard deviation. And then finally, there is a quantity called the sample, or I keep saying sample, sorry, the standard deviation of the mean. This is different of the standard, the other two standard deviations, because the other two standard deviations, you're talking about how much error there is in a single measurement, as in, I take a bunch of measurements and this tells me the error in one of those. This instead tells you how close your sample average is to the true average. So it's telling you the error in your mean. So if I take several measurements and take the average of them, I take the mean of them, this is the error in that mean, hence standard deviation of the mean. And most importantly, as I take a lot more and more measurements, this one actually becomes 0 because there effectively is no difference between my mean and whatever the true mean is. So how do you practically make this sort of calculation? Excuse me. So let's just suppose that we took 5 measurements of a temperature with a nice digital thermometer that gives me a readout to 1/10 of a degree, right? So you take these values, and usually you want to do this in some sort of program. For example, here, what's going to be shown is Excel, but Google Sheets should work, whatever sort of spreadsheet software you have. And then also there's a number of actual scientific applications that do this sort of thing for statistical analysis. But basically, the first thing we want to do is take the sum of all of these values, right? Next thing is you divide by the number you had to calculate the mean, right? And then fairly obviously, this is just stepping through what the equation for the standard deviation is. I'm going to take the difference between each one of my values and what the mean is. So how far off of each of these values are each of these values from the average value? And because I don't want to add these together and have them cancel out, because an individual measurement can be higher or lower than the average, I'm going to square them so I don't add a bunch of pluses and minuses together and cancel them out. And then finally, you're just going to sum up all of those values. You can then divide by the n minus 1. And then take the square root of that number. And that is the standard deviation. So you could go through all of this, but most programs actually have the standard deviation function built into them. And I'm sorry if this does not show up too well on the screen, but feel free to download the slides. This is what the functions are called in Excel. In different programs, they're probably going to be called different things. But the key thing to be careful of is there's going to be multiple functions called standard deviation because, like I said, there's also the population standard deviation and the sample standard deviation. In Excel, you can see there's these two functions, stdev.p and .s, and those mean exactly what you think they would mean: the population standard deviation and the sample standard deviation. And you can see if I just call that function on my original set of values, you get the exact same result. So the function does exactly what you think it should. So you could also, excuse me, take the example of what if I didn't have a nice electronic thermometer, if I had just a simple glass bulb thermometer that I can maybe read to 1/2 degree, maybe only a 1 degree. Well, now if I'm rounding that, I'll probably get the same value 5 times. And if I repeat the calculation, I just get a 0 for the standard deviation and the standard deviation of the mean. And the question then comes, well, does that mean my measurement has no error in it? Well, no. I mean, obviously, there has to be some error. In fact, you've used a worse instrument, so you would expect there to be larger error. So, it's the same sort of thing where if I measure something with a ruler marked down to millimeters, I can't really tell anything about the length more than millimeters. And the key point here is the standard deviation only talks about the random error. When there's the entire other type of error, in this case, which is the much larger source of error, the systematic error. So in the case of our thermometer, we want to say the systematic error is at least as big as 1/2 degree, because if the thermometer was off by anything smaller than that, we wouldn't be able to tell. So what that means is you can't forget about your systematic error or uncertainty. You have to have an estimate for it and then add it to your random uncertainty to find what the total error is. Well, how do you add errors? I mean, the simplest solution would just be to have, 2 different errors and assume you just add them up. But in particular, when you have random error, you do not expect both of those to be at their max values. So in fact, you will overestimate the errors. You just add them straight like that. You can instead do what's called adding in quadrature. And all that means is you square the two values, add them, and take the square root. However, the strict mathematical proof of why you can do this assumes that those two variables whose error you're talking about are independent from each other, i.e. they don't depend on each other at all, and then also that they are following a Gaussian or a normal statistics. But it's usually a safe assumption to say that they are. So for example, in the case we just discussed, I have systematic error and random error, and I want to add them together. Well, for the bulb thermometer, it's easy. The random error was 0. And you can see that when you do that, well, you just get what the systematic error is. And usually when that is happening, you say that, you know, you're dominated by this systematic error. The systematic error is much larger. And that means you can pretty much ignore the random error. And this is also a way you can decide how many measurements you're going to take. Since taking additional measurements only reduces the random error, once that random error is small compared to the systematic error, there's no point in taking additional measurements. You're not gaining any more information. For a less trivial example, you can look at the digital thermometer, and in that case, we assume, okay, it goes down to 0.1 degree. Let's assume that's the systematic error. A better method would be to look at, for example, the manual that came with it, see if there's a specified error there. But if you don't have any additional information, you want to at least assume the smallest digit as the systematic error on there. I do the same thing, and I get a value that's close to the random error, but it's a little bit bigger because there is still some systematic. And in fact, you can make a generalized version of this equation. And that is what is known as propagating error or propagation of error. And what that lets you do is if I have some random function or some value that's calculated from a whole bunch of other things, say, for example, the volume of a box, you can calculate what the error is in that final calculated value from the errors of all the things that go into calculating it. So the error in the final thing is you just add in quadrature what's called the partial derivative. So this df dx, that's a partial derivative. And that is basically taking the derivative of the function with respect to the variable x1 and treating everything else as a constant. Now, obviously, some of you probably have not gotten into calculus yet, so you don't know what a derivative is, but this is not a calculus class, so you should feel free to just look up the derivative, of whatever version you need. And then you just multiply that partial derivative times the error in the variable. So if I have, we'll go through an example in a second, and you just do that for all of the variables that are in your equation. Like I said, this is a generalization of the addition formula, and the same caveats apply. All of the variables, x1, x2, x3, have to be independent of each other. So if they depend on one another, this doesn't work. And you're again assuming you're following some kind of normal distribution. So for an example, let's say we have a rectangular box or object, and I want to both calculate the volume of this box and I want to know the error in that calculation. So assume it's 10 by 12 by 5 millimeters. And again, let's take the example of a ruler where we're probably not going to notice any random error, and it's just going to be the systematic. So I'm going to say that I can read this ruler down to half an increment, so half a millimeter. Okay, well, the formula for a rectangular prism is just length times width times height. So 10 times 12 times 5, 600 millimeters cubed. Fairly straightforward. So now I need to calculate what's the error in that volume. Well, that volume is a function of the three different variables, so length, width, and height. So those are what were our just generic x1, x2, x3 in that previous equation, right? We've just replaced them with real variables. So the error in the volume is this entire term under the square root. So I take the derivative of volume with respect to length, multiply it by the error in the length, and do the same thing for the height and the width. So just to, again, feel free to look up what the actual partial derivatives are, but in this case, the partial derivative with respect to length is just width times height, right? And similarly for the width and height. So the final equation you get when you do this is this one on the bottom. And one thing you should notice is that each of these terms within the parentheses have units in volume, right? Because the error in length is a length. And that makes sense because the error in volume should be in volume. So if we plug in the numbers, you know, you'll get like about 70 millimeters cubed. So for your reference, on the LACES website, there is a resource under Unit 5. It's a PDF that just has a bunch of like sample functions, and you know, here's the partial derivatives of them, and here's what the error, the final resulting error equation would be for them. So we discussed the Gaussian distribution, but that's sort of implies that there's other distributions. And there, in fact, are a whole bunch of distributions. But most likely, a lot of those you're not going to run into unless you're doing some very specific things, except for something that is called the Poisson distribution. So basically what this is if I'm doing some sort of counting process of events that happen at a random rate, but over a long period of time they average out to a certain rate. You know, and you'll encounter this if you're doing some sort of, if you're measuring the number of radioactive decays happening, if you're counting individual photons from a bunch of, you know, astrophysical processes, if you're counting photons from a particular star. But it also applies to, for example, river flooding. You know, if there's a certain number of floods every 100 years, well, what's the chance I get one flood in the next 100 years, 2 floods, etc.? So again, it has a particular mathematical formula, and when you plug in the appropriate values, what this tells you is what is the chance that I'm going to have one flood, two floods, no floods, K floods over the next 100 years if I have this many floods, and that particular symbol is called a lambda. It's what's usually used for that, but it's just the average rate. So if I had an average of 5 floods in every 100 years, it would be 5, right? So one thing to note, as opposed to the normal distribution, this is not always symmetric. So you can see here, when the average value, lambda, is small, it's very, very lopsided. But as it becomes larger and larger, it starts to become more symmetric. And also, obviously, the average value, which is what lambda is, shifts. So the center also moves. So if I go high enough up to 25 and I look at a normal distribution, it looks pretty close, but you can see here on the left-hand side, it's a little bit lower. One thing to note here is all of the possible values are whole numbers because I'm counting something. I can't have 1.5 radioactive decays. I can't have 1.5 floods. I either have a thing happen or not. So like I said previously, we usually assume the Gaussian or normal distributions. But why do we do that if there's other distributions? And you don't need to probably know the specific math behind it, but part of the reason is once we take a large number of random variables or random samples, the distribution will become Gaussian as that number goes big, as that number becomes large, as you say in English. And there's also the fact that those error propagation formulas apply to the Gaussian distribution, and that is useful math for doing error analysis. So in general, we want to assume it's a Gaussian because that's the easiest case to deal with unless we have evidence that it's not. And it turns out that's a pretty good model for a lot of actual physical measurements. And that has to do with the fact that if you have many, many random errors adding up, it will become a Gaussian. And that is something that's called the central limit theorem, if you wanted to go look that up, but by no means do you need to know the proof of that. So another important thing that goes into this error analysis is how do you actually report your measurement and its associated error? So one thing that doesn't make sense is if you think your measurement is only good to 0.5 millimeter, the error is 0.5 millimeter, why would you report its average down to 1/100 of a millimeter? Those decimal places that are way smaller than the error are pretty meaningless because you've already said, well, I don't really know if it's 12.5 or 11.5. So the 0.003 is something that you can just drop. So the standard practice is to either round the error to 1 or 2 digits, and then you round the measurement to whatever decimal place the error is. So for the example above, you would round to 12.0 plus or minus 0.5. One key thing to note, though, is you don't want to round intermediate values for your calculations, right? If you're going to be doing multiple calculations with the value, keep many decimal places and use all of those and only round at the very end. And you want to show how you've calculated this error is what you mean by that plus or minus. So you want to be explicit with your equations and show your work, just like you would in any other science application. So functionally, how do you put all of this stuff together and get some, use it on your data that you have hopefully collected from your SkeeterSat? Well, let's assume first that we did some initial measurements with a glass bulb thermometer, and it was similar to that case we discussed back in the standard deviation, where we basically couldn't see any random error because the scale on our thermometer was too coarse. We could only read out half a degree. So because of that, you can sort of make the argument that, well, I only need to make one temperature measurement for each data point, because repeated temperature measurements are not telling me anything further. I'm just going to get the same number, and the error is going to be the 0.5 because I'm using a bulb thermometer. But you still want to make repeated measurements of the frequency at each one of those temperature points. So again, before you start, you want to estimate, or at some point you want to estimate what your systematic frequency on that temperature or on that frequency measurement is. So you can look at things like what is the pixel size in the spectrogram software and how wide are those dark patches to get an estimate in hertz at how big that is. In this case, we've assumed I've done that, and what I got was 11 hertz. So I then decide to make 5 independent frequency measurements. So basically 5 different beeps. I looked at the first harmonic and the second harmonic, and I calculated the difference between all of those. So then the difference between those is your fundamental frequency. We do the same thing like we did in the standard deviation example. You calculate the mean. I calculate the standard deviation, and then I calculate what the standard deviation and the mean is. And then I use the mean as my value for the data point. And then I add the systematic error to the random error for that mean, which is the standard deviation of the mean. And I get a single data point that has uncertainty both in frequency and in temperature. So this just gives me like one data point that I'm going to use on my fit. So now you want to repeat that for multiple temperatures. In this case, I've done it for temperatures ranging from 5 to 95 degrees. And when you do that for all of the different frequency and temperature pairs, you get an error for both. You get an error in the temperature and you get an error in the frequency. In this case, all of the temperature errors are the same because, like we discussed, you're dominated by the scale markings on that bulb thermometer. But you can see there's actually a decent amount of variation on the frequency error. But you can see that you don't get a value lower than 11 because 11 is what we had estimated as the systematic error. So we're always adding a little bit of random error to that. So once we've done that, we want to plot all of the points. And usually for this sort of thing, you want to use a scatter plot. You can do this in Excel, but like I said before, there are many different pieces of software that you can use to do this, to make your graphs and do fits. So because our ultimate goal is to basically get a readout of temperature in terms of what the frequency is being outputted, we want temperature as a function of frequency. That means we pick frequency as our x values and temperature as the y values. So once we have all of the points plotted, we need to add error bars. So in this case, our errors were symmetric. That means you have, so normally you have a positive and a negative error bar. So either to the right and the left for the horizontal, or up above and below. And sometimes you may have a larger plus than your minus. It may be like +3, -1. In that case, they're not going to be symmetric, but in this example, they are, so we just use the calculated errors as both the positive and negative error. And additionally, a lot of your software is going to have an option that lets you pick, just put in a percentage. A lot of times you have different options for specifying these error bars, and there's some that'll let you put in like a fixed value, a percentage, or a standard deviation. Sorry. But what you actually want to do is one that lets you specify specific values because you've calculated them, and you want to be able to specify for each individual point. And how you actually do that is going to depend on what software you're using. In Excel, you pick the option that lets you specify them, and then you just drag the selection of the errors, and it assumes they're in the same order as you did when you specified the points. But the key thing is you want to have both horizontal and vertical error bars, because you had error in both frequency and temperature. And sometimes, if your error bars are very small, the default point size may be too big, and it'll be covering it, and it'll look like you didn't do any error calculation. And then the first thing that somebody's going to ask when they look at your plot is, well, what happened to your error? Are these all perfect measurements? And in that case, you may there's a few things you can do. You can reduce the size of the individual marker points. You can also add a caption if they're really small and there's no way to make them show up in a meaningful way. What you can do is just say something along the lines of error bars excluded for clarity, or something like that. So after you've added your error bars, next thing you want to do is add a trend line. So if you look at this data, it's pretty obvious that it's not a linear fit. It looks like maybe it could be linear up here, but then it just kind of dips off. So ideally, you would have, either by analyzing the circuit ahead of time, or knowing the theory of operation, or maybe just having a pure physics theory, you would have an idea of what sort of behavior you're expecting and go into it looking at that fit. However, that may not be the case. You may not know. So you can look at, which of the different types of fit will match. But again, like we discussed in the previous lecture, you don't want to just go an arbitrarily large polynomial, because once I put enough constants in an equation, you can manipulate it and basically perfectly go through every single one of those points if you put enough. So you want to minimize the number of constants. In this case, what I did was I said, well, that kind of looks like a logarithmic function, so let me plot a log fit to it. And then a key thing you want to remember to do is also show the equation on the plot so that people can tell what the actual equation is. Alternatively, you can give the equation in like the text of your report or in your presentation, whatever you're using this for. So once you've done that, you want to finish the plot and then start working on conclusions or maybe go on to other analysis. So obviously you don't want to forget the usual stuff that you put on a plot: axes titles, units, a plot title. But a good quick check of your fit is about 2/3, and this is a very rough about, of your points with the error bars should overlap with your line. And where that comes from is, if you remember, going all the way back to the Gaussian distribution, we said that 67% of the measurements should be within this region. So that is where that about 2/3 come from, because 67% is about 2/3. So if it's, way less than 2/3 of your points overlap, well, maybe you picked the wrong type of function. Alternatively, you may be underestimating your error. It's fairly easy to miss, to have a systematic that you didn't think about until you're like, well, this isn't quite right, let me think about it a little harder. Alternatively, you can have too many of your points line up. So that may point to the fact that you're doing something called overfitting. You've basically put too many free parameters, and you can always adjust them slightly to make it go through as many points as you want. Another thing that may be the cause of that is you've overestimated your error. And in fact, the way that a lot of manufacturers specify their instruments is they're actually giving you a guarantee of it's accurate to this amount, right? Because they're trying to market their equipment and show how good it is. So they, alternatively, they may just be giving a, hey, it may be better than this, but we're going to say it's at least this good, rather than using like a scientific definition of error. So a lot of times when a manufacturer specifies their error, they may mean something different than what you would mean in a scientific context. And that is it for this section.